Hello everyone, my name is André. I'm from Federal University of São Carlos, Brazil. I'm going to present the paper Event Race Detection for Node.js using delay injections. This is a joint work with Anders Muller from Aarhus University. So this research is in the context of Node.js, which is a JavaScript runtime launched in 2009. Its main goal was to bring JavaScript on the server side. So with Node, it's possible to develop server-side web applications, microservices, desktop mobile apps, and so on. Node comes with a core API, which is composed of built-in modules that can be used for file manipulation, networking, cryptography, and so on. So Node also has a manager called NPM. Today is one of the largest software ecosystems in the world with many libraries and frameworks. So many software applications are powered by Node.js. Node adopts a single-threaded asynchronous model, so to avoid blocking the main thread, time-consuming tasks like I/O, compression, cryptography are performed asynchronously. So such tasks are started with async calls, and their results are processed through JavaScript callbacks that act as event handlers. So Node.js applications are subjected to event races. So the event race uh, happen due to the timing of the background workers and event handlers that cause non-deterministic callback interleavings. So such interleavings may provoke fault behavior, in other words, harmful event hazes. So it may cause applications to crash and other problems. Uh, Such bugs are prevalent in Node.js application as it has been investigated in the literature. A research problem is that different callbacks may execute it in different orders or interleave, but ordinary runs, like the ones shown in the figure, tend to show very few variations or no variation at all in the callback interleavings. So we want to provide an approach for dynamically exploring or fuzzing the interleavings so that we can expose harmful races. A key observation in this research is that a Node.js application is composed of application code and library code. Both application and library code interacts with Node.js built-in modules that are used to access features related to networking, file systems, and so on. So the source of asynchronous behavior comes from the core API of Node.js. Our approach explores this observation by injecting random delays around the asynchronous functions provided by the built-in modules. So the approach we propose is called NACD, and its main idea is to fuzz the scheduling of event handlers by dynamically injecting random delays around both before and after the asynchronous functions in the built-in modules. So this is achieved purely in JavaScript, and NACD is divided in two components. Uh, a model that defines where injects the delay, and a runtime systems that define how the delays are injected. To create the model, we first study how asynchrony is used in the built-in models. So the model we define is basically a collection of a sync class, and a sync class represents a module that has some async behavior. A sync class also contains properties that describes functions or objects. We notice that different forms of asynchrony, of asynchronous behavior occur in Node.js built-in modules, and we group them as code partners. In NACD, the model is stored as JSON files. An example of a code partner here is the simple callback that is illustrated next. In figure A, there is a JavaScript code of a function read file of built-in module fs. So this is an ordinary example with a callback. So we ask it to read file.txt, and it defines a callback to be called when the result is processed. Uh, its model representation for this case is illustrated in figure B. We have here the module name fs, and here we have the function read file that is a property of this module, and here we defined that this function employs the code partner simple callback. Another example of a code partner is returned promise. Um, Here in figure A, we have a resolve function here that is called in two different contexts, and resolve function is from the DNS promises, and this function returns a promise that is a future object that says when an asynchronous behavior is supposed to be ready. Um, its model is represented here in figure B. Function resolve, in this case, from module DNS.promises, employ the code partner called returned promise. There are other code partners that we defined in our model, but a special case that we mention here are the event emitters. Event emitters are special objects used in built-in modules in which callbacks are associated with named events. So in this case, for the example, in this figure, there are three callbacks: data, end, and close of object read string. So these callbacks, uh, while these callbacks may be scheduled non-deterministically among them, the callbacks should be executed in the same order. So to represent this case, we mark them in our model as connected callbacks so that NACD can handle them properly. There are other code partners described in the paper. It's also possible to have functions combining different code partners. For example, a function has a callback, but also return an object with a synchronous behavior. So currently, NACD model is composed of 19 JSON files with 46 async classes and 424 properties. Using the model previously presented, NACD runtime system installs hooks on the asynchronous operations we intended to delay. So it intercepts when the application access the core API we module. So this happens at runtime and on demand. So to do so, NACD modifies the Node.js module system and, and installing proxies using JavaScript native uh, APIs, proxy, and reflect. Uh, so basically, NACD adds some hook functions, in this case, hook functions called onRun, that are invoked right before an asynchronous operation is about to run. In figure, in this algorithm, op is the asynchronous operation connected, say if the op is a connected callback, and object ID defines the objects associated with the operation. So if it's not a connected callback, it calls functions that is decided simple delay. Otherwise, it calls decided connected delay, passing the operation and the object ID. These functions deals, this first function that is decided simple delay deals with operations that are not related to connected callback. It simply makes a random choice here, and if delay is true, right? So it injects a delay here with some random timeout. Otherwise, if you decide there is no delays, it runs immediately. The other case is when the operation is a connected callback. So we need to handle the expected order of an event emitter. So here we have the function decided connected delay. So to do so, NACD keeps a queue for each event emitter or a queue per object. And we use this queue to preserve the order in which the callbacks, the connected callbacks, are schedules. So in the example, in this example here, NACD assigns to objects read string an ID, in this case the ID 10. When callbacks for event data that is called twice and uh, events and close are scheduled, they are added to a queue, and the queue is identified by the object ID. So using this queue, NACD can, for example, inject a delay in the first callback CB data while keeping the original order in which the callbacks were initially scheduled. In the evaluation of NACD, we compare NACD with two state-of-the-art tools, NodeFuzz and Node Racer. To support the comparisons, we adopted 23 benchmarks used in the literature. Uh, the benchmarks are all based on real-world race bugs from open source projects. Then we investigate 3 research questions. In the first one, we look at how many times each tool can reproduce a racebook in 100 runs. We called this metric bug reproduction ratio. Question 2 assess the number of runs until the first failure occur. Finally, question 3 analyzes the overhead for both elapsed time or wall clock time and CPU time. After analyzing the researches, after analyzing the results to question 1 that says to what extent is NACD capable of reproducing race bugs in Node.js application, we observed that NACD is capable of uncovering race bugs with false alarms, being on average more effective than that state-of-the-art tool. Particularly, NACD has had the best bug reproduction ratio in 78% of the benchmarks. In question 2, we intend to answer the question, how many runs does NACD take to review a race bug? We observed that to trigger the first failure, NACD perform as well as or better in 82% of the benchmarks. When considering the aggregate results across all 23 benchmarks, NCD can provoke the phase failure, taking an average on 2.5 runs. Finally, question 3 aims to answer the question, what's the overhead imposed by NACD? So we compute the overhead with respect to running the benchmark using vanilla Node.js. By looking just at the overhead, NodeFuzz and Node Racer exhibited lower elapsed time when compared with NACD, while NACD consumes lower CPU time. Some benchmarks manifest event races as timeouts, so we also analyze the overhead in relation to the bug detection rate. In these cases, NACD presents significant better performance in both elapsed time and CPU time. Concluding, event races may cause many errors in Node.js applications, and exploring callback interleavings helps to uncover such errors. Our key idea is that most of the async behavior in Node.js originates from its built-in modules. And NACD, to implement this key idea, NACD is fully implemented in JavaScript with 2 components, an extensible model and a runtime system that can be used to inject delays in the functions of built-in modules. And experimental results shows that we can uncover race bugs more effectively than state-of-the-art tools. And if in future, we intend to adapt NACD to other platforms and the platforms that share a similar single-thread event-driven architecture. More details about this research can be found in this link. You may also scan the QR code There you have pointers to the preprint, the source code of the tool, as well as the replication package. Thank you.